All right. Well, good morning, everybody. And welcome to the Minnesota Stormwater Seminar Series. My name is Maggie Karschnia, and I will be your moderator for today's seminar. So we've all experienced the challenges of this growing population in Minnesota. We have more and more urban development happening and fewer spaces to put our best management practices. We are going to start off today with a great presentation on addressing some of these challenges. It's a recently completed research project funded through the Minnesota Stormwater Research Council, followed by a panel discussion. So if you haven't been to a seminar series before, this occurs monthly, typically. We bring in national, state, and local experts to talk about these key stormwater issues that we all face here in Minnesota. Now, this work and this seminar series could not be done without the support of our host, St. Anthony Falls Lab. Specifically, I want to give a call out to Dr. Andy Erickson and Dr. John Gulliver, who really keep this seminar series going and thriving. So thank you to those. We also are supported by multiple entities for financial support. This includes the Minnesota Stormwater Research Council, who receives donations from cities, watershed districts, consulting firms, and others. This helps amplify our research work, and we really appreciate that contribution. Now, a large part of our work for the research as well as the seminar series is funded through the Clean Water Land and Legacy Amendment. Now, this is appropriated through the Clean Water Council, and we couldn't do this work without them as well. And I also want to give props to the Water Resources Center, which is where I'm based out of, as well as St. Anthony Falls Lab. So if you missed an older seminar series and wish you could have attended, we have all of these online. So we have a YouTube page that lists all of these different videos. You can also just go to the seminar series webpage, and we have descriptions and video links there as well. This one will be posted shortly afterwards too. And I do want to highlight that we have another seminar coming up here in just a couple weeks. We are inviting in one of our national experts. So it's Laura Fay. She's flying in from Montana State University. She's going to be talking about using winter chloride management to reduce impacts of winter maintenance operations. It's going to be a great presentation followed by a panel discussion. And another one that I'm really excited about, we don't have a date for yet, is our June seminar series. So we're going to be highlighting 2 recently completed stormwater ponds projects. Ponds are such a huge issue right now. And that'll be posted shortly for registration. Now, if you want to get registered first and hear about things first, you want to be joining this Stormwater Updates newsletter. You'll get a link to this afterwards in the follow-up email, but this is where you can hear about what seminar series are going to happen, all the great research that we're doing, as well as other important stormwater information. So, also a little housekeeping before we get started. For those of you joining us virtually, we want to hear all of your questions too, so please use the Q&A feature of the Zoom in order to ask your questions. And if you like the question that somebody has asked, please give it a thumbs up. The more upvotes a question gets, we'll be answering those first. And if you have any technical issues, just use the chat feature. Now, for those of you in the room that have joined us, if you have a question after the presentation, just raise your hand. But please wait to ask the question until I bring the microphone to you. Otherwise, the folks online can't hear. Now, if anybody's looking for professional development hours, you'll get information on how to get those after in the follow-up email. So that leads me to the seminar series today. So like I said, we are going to have a great presentation on the research project. We'll do some Q&A right afterwards. And then from 12 to 12:15, we are going to take a brief break to grab some food, take a bio break, and then we're going to come back online here at 12:15 for a robust panel discussion. So today's seminar focuses on turning tight spaces into big solutions, testing a high-volume stormwater filter at Rosland Park. So we've all had these challenges in these tight urban settings. This one builds on previous research, takes a look at some of the innovative media solutions that have come out, and it tests 3 different types of media in this high volume setting. I am really excited to hear the results of this research, and I am so pleased to introduce our presenters. We have Dr. Andy McCabe from Barr Engineering, and we have Erica Sniegowski from 9 Mile Creek Watershed District. So let's welcome them with a round of applause.
Wonderful. Okay. Thanks, Maggie. Perfect. Okay. So already did introductions. I'm Andy McCabe. I'm from Barr Engineering. Here with Erica, and we're going to be talking about the stormwater filtration system at Rosland Park. Before getting started, we've already heard a little bit about funding, but for this project specifically, the work that we're going to be talking about today was a performance monitoring program, was funded by the Minnesota Stormwater Research Council through the Clean Water Fund, and it was also supplemented with funding from the 9 Mile Creek Watershed District. And then a project like this, of course, doesn't happen by just 1 or 2 or 3 individuals. It takes a whole village to do it. So this is just our project team just looking at those individuals who had a hand in the performance monitoring program. But of course, the filtration system, and we'll get into the details of it, took a whole engineering team. It takes a lot of people to get a project like this to go. So I just want to give a thank you and an acknowledgement to all of those people that were involved. Okay, so where are we going? So first few slides, Eric will run through the background and kind of the higher level picture of how we got to the point of putting in the stormwater filter. I'll go over the results of our actual research program, the performance monitoring results. We'll look at the operations and maintenance that we've had to do over the last 3 years. We'll look at the cost benefit, scalability, and then we'll have some closing remarks.
Thanks, Andy. So as Andy mentioned, I'm going to provide high-level context and background of our decision to install the high-volume stormwater filter in partnership with the city of Edina. So for those of you that are familiar with the Twin Cities metro area, the project location is just off the southeast corner of Highway 162. And I know we have some folks that are joining from outside of Minnesota. So this project location is in the city of Edina. And Edina is a southwestern suburb in the Twin Cities metro area of Minnesota. And so this filter is located in Rosland Park, which the city of Edina owns and operates. And the filter is located in between Swimming Pool Pond and the north basin of Lake Cornelia. And it's in a fairly heavily used park that has amenities like disc golf. It has a park right there, and it's also right near the Edina Aquatic Center. So why did we need to think about installing a filter in the first place? The big picture is Lake Cornelia is unhealthy. It is a shallow urban lake that receives a large volume of stormwater runoff. If we look at the graph that's located right here, what you see is summer average total phosphorus. The darker orange bars are for the north basin of Lake Cornelia, and the lighter orange bars are the south basin of Lake Cornelia. So there are 2 basins to Lake Cornelia that are connected via a pipe. And what you can see from this graph is, since the monitoring data that's displayed from 2003 is that we are above the state standard for total phosphorus in a shallow lake. So we have an unhealthy lake with a lot of phosphorus that's fueling algae blooms, and we are seeing blue-green algae blooms in this lake as well, quite frequently. So poor water quality, highly impervious watershed with a lot of watershed stormwater runoff. And not only that, there's also a 2018 total maximum daily load that identifies phosphorus and has a phosphorus reduction goal for North Cornelia. And beyond phosphorus, there's other water issues with this lake. We have a poor aquatic plant population and curly-leaf pondweed, an invasive aquatic plant in the lake. And then we also found that we had a lot of goldfish in the lake. And for those of you that aren't familiar, goldfish are an invasive fish, and they act a lot like carp in that they root around in the bottom of the lake and they stir up sediment and release phosphorus in the water. So a lot of problems going on in the lake. Beyond the filtration vault that we're going to talk about today, there were other management strategies that we looked at and addressed. So again, the primary phosphorus sources to Lake Cornelia include watershed runoff, so our external sources coming into the lake, but there are also in-lake sources. So we have phosphorus loading from the sediments in the lake. And so since 2019, we've been working on some improvement strategies as the watershed district. And so we did an alum treatment in 2020 to minimize sediment phosphorus loading to the lake. The city of Edina had also been doing curly-leaf pondweed treatments, which the district took over in 2023 and 2024, and we've been doing curly-leaf pondweed treatments since. And then we've also been doing goldfish management. Again, I mentioned we have a lot of goldfish in the lake, and I was going to share the number of goldfish that we've taken out because it might astound some people. So between North and South Cornelia and between 2023 and 2024, we've removed 67,000 individual goldfish from these two lake basins. And that amounts to about 5,000 pounds of goldfish. And fortunately, we have seen some response in the native fish population. So we're starting to see a better, healthier native fish population in the lake as a result. And then I also wanted to mention that the city of Edina is doing enhanced street sweeping in the sub-watershed as well to manage external loading to the lake. So we're talking about BMPs and tight urban spaces. And so just to give you some context to the sub-watershed that's draining to Lake Cornelia and Swimming Pool Pond is there's about 410 acres that drains to Swimming Pool Pond. And so that's all highlighted in yellow. And it's very densely urban. We have Southdale Mall, we have a medical complex, so a lot of hard impervious surface, and we have part of Highway 62 that's draining to Swimming Pool Pond. And so that's about 40% of the tributary area to Lake Cornelia. So again, we're dealing with these highly urban spaces, and we have to figure out how can we manage the external load coming into these water bodies. So what were then the objectives for the watershed district in partnership with the city of Edina to install the Rosland filtration system? So I think you've probably already realized we are really trying to address the external phosphorus loading to Lake Cornelia so we can have a healthier water body. We are also trying to manage installing a best management practice in a small footprint. One of the desires from both the city of Edina and other stakeholders was to preserve green space in the park. And so we really needed to minimize the footprint of the filter as we looked to design and install it. And then finally, we are looking to utilize the existing storage capacity to provide a near continuous water source to run the filter. And so what I really mean by this is we are looking to not only run the filter when we have stormwater runoff or rain events in water to run it that way, but we are looking to use a water body to be able to run it continuously. So how the filter operates is under normal water levels. It pulls water from Swimming Pool Pond. And then when we have lower water levels, it's actually able to pull water from Lake Cornelia. The system was constructed in 2021 through early 2022, and we got it started up and running in the summer of 2022. And then in August is when we started the heavy-duty monitoring to really understand how is the system performing, what's it doing. And again, as was mentioned, this work was supported by the Minnesota Stormwater Research Council and funding from the 9 Mile Creek Watershed District. And I definitely want to call out again that we had a grant from Hennepin County through their Opportunity Grant Program and the Board of Water and Soil Resources through a Clean Water Fund grant for the construction of the filtration vault. So we had about $850,000 in grant funding for the installation of this vault as well. And with that, I'm going to pass it back over to Andy so he can get into the details of the construction of the vault, how it works, and the monitoring, which I'm sure you're all excited to hear about.
Thank you. Thanks, Erica. Okay, so on this slide, we're going to just take a quick walkthrough of the process flow of the filtration system. So this is a drone image taken in October, so a few months after it was constructed, construction was complete. So just to walk through where we are, so starting up here, this is swimming pool pond. Intake structure here comes down to a manhole where we've installed a fish screen and a T that comes over here to this little concrete pad where we have a filter vault. Inside is a submersible pump that's capable of pumping out about 400 gallons per minute. It then flows via pipe through another vault here that has a magnetic flow meter so we can monitor the inflow and flow. Still underground in a pipe, coming over here to a vertical standpipe that we've called an aeration manhole. So what this is it's a vertical pipe where the water is allowed to cascade 3 feet down or so just to aerate it. And then from there, now we're flowing again through a pipe. I don't see my cursor, but it's here somewhere. We're still following the red lines. Then we go through a manifold through 6 anthracite pre-filtration cells. And then the green, blue, and purple, those are our reactive media cells. So that's what's actually doing the phosphorus absorption. And then everything from there is gravity. So we go from the green, blue, purple cells down through this sort of teal pipe to Lake Cornelia. And the last thing that I just want to point out on the process flow is right about here, you'll notice this other red line. So in the anthracite, its main purpose is to remove suspended material before we get to the reactive phosphorus absorption media. When that anthracite basically gets full, it is full of all the TSS and other debris that we're removing, that water overflows. And the intent with it is that an operator can easily drive by the system and say, oh, I see lots of flow coming in the overflow, time to do a backwash. And we'll come across these, but just to point out the naming convention, so the locations, we'll see these on some of the charts. SW is surface water, 0 is our influent, A is pre-aeration manhole, B is after the aeration manhole, 1, so we call cell 1 the anthracite pretreatment cell, and then 2, green, blue is 3, skipped 1, and then purple is 4. So SW 2, 3, 4 for the actual effluent from each of the filtration media. Okay, so we just did this sort of walkthrough, but just to give a little bit more granular context. So here, anthracite, again, we have it split into 6 different cells, and the reason that is so that we can perform a backwash using the forward flow pump. So when we're doing a backwash, what we're really trying to do is we're trying to fluidize that bed. And so typically you need to have a higher flow rate than your forward flow rate to do that. So if we're going 400 GPM forward, to do a backwash, we need to split it, and just by the math, how the calculation works out, we figured we needed to split that cell into 6 different cells so we can do a good job backwashing the media with a forward flow pump. And backwash in this case, it is a pretty manual operation, so we have to actually physically go out, turn off the forward flow valves, and then manually turn on the pump for each cell, and do that for anywhere from 15 to 30 minutes or so per cell. So the media, I think I mentioned already, is anthracite. So anthracite is a hard coal-based material. We use it a lot in the drinking water treatment area. It's in lots of mixed media filter cells. So if you see a mixed media filter cell, typically there's 3 layers. There's a sand, garnet, and then anthracite. And anthracite sits on top because it's less dense. And it sits on top and it's a little bit coarser, right? So you don't plug it up before it goes through the finer material. In this case, we're just using anthracite, so we don't have a mixed media filter cell. It's just anthracite. Then we go into, oops, wrong button. Then we go into our color coordinated cells here, so just going through the list. Our first cell has granite sand with zero valent iron. So zero valent iron is just, it's the iron in iron enhanced sand filters. It's just shards of iron. And granite sand is just a little bit coarser sand than typical C33 sand that you might see in an iron enhanced sand filter, but we're trying to do basically the same thing, right? So we're mixing iron with an inert sort of carrier media that holds the iron in place. The next cell, the blue one, is a CC17 mixed with ZVI, so zero valent iron again. CC17 is calcium carbonate. It's a pretty coarse aggregate material. We sourced it from Superior Minerals and Savage, and I love this. The media is actually called beak and bone. So if you're looking for it, I asked the guys, I was like, what is this, crushed up beaks and bones? No, it's a feed supplement, and maybe y'all knew that, but I was pretty astounded. So it's a pretty cool media though. And then the last one, the purple, granite sand, so it's the same inert media as the first green one. It's a composite media that we sourced from Delta Adsorbents, so it's AAFS50, and AAFS is activated alumina, and then FS is ferric sorbent. So it basically has activated alumina, which is aluminum oxide Al2O3, and that's the support, and then you have a coating of iron oxide on the outside. So it's a media, they sell it for all kinds of things. So you can use it in stormwater, you can use it for remediation, because ferric is actually really great for absorption of metals and things that you might see as groundwater contaminants. So all three of these cells, so the green, blue, and purple, they run in parallel. So it goes down through the anthracite, and then we come out through each of these media cells. This gives you a profile view of the filtration system. So this is an actual picture, right? So this is as if we are looking sideways at it and we slice away the ground. So we have our influent water coming in on the left-hand side. That flows over a weir structure down through the anthracite. And we have an underdrain system, and then with perforations, of course, and then flows over and then up through the reactive media, and then out, and then gravity drains to Lake Cornelia. And just to point out, right, we're collecting samples through this monitoring program at the influent. So, and I already mentioned this, but before and after aeration, we have actually, to collect this sample, we have a standpipe in one of the media cells that runs all the way up here. So we're collecting water before it's going through the reactive media. And then to get the last bit, we just collect a water sample as it's overflowing out the effluent. The media depths here, so it's not drawn to scale, but this is about 2 feet of media. And I'm saying it's not to scale because we got about 3 feet of head between these two cells. And the purpose for the downflow upflow configuration is really just to take advantage, because we don't have a lot of head, right? So we're just taking advantage of the small amount of head that we have to push the water all the way through the media. Okay, this is a pretty cool thing. So we have a control panel and an HMI, basically just to control the pump. It has some cool readouts on it, so we can see the water elevation both within the wet well that houses the pump, as well as the elevation on top of the anthracite. And then it gives us the flow both influent and of the effluent from each of the reactive media cells. And then the other cool thing about it is we have a remote HMI, so this is hooked up to a cellular service so that we can then access it on the phone, and you can turn on and off the pump as you need to, see if it's operating, which is really helpful for us because that's our main purpose here is monitoring the cell. So we would check, hey, is it operating? Does it look like good conditions? Let's go collect a sample. Okay, so routine maintenance. So we've sort of walked through the process flow, and now just to orient this picture, right? So I mentioned there's a T coming off between the drainage pipe that goes from swimming pool pond to Lake Cornelia. We installed this T that has a fish screen that protects the pump before the water actually goes through the filtration system. So this is the fish screen right here. So it's just a removable, it's expanded steel, sheet of expanded steel, and you pull it out, clean it off. The two main routine maintenance operations that we have to do with this is backwash to the filtration cells. And most of the maintenance was done by the city of Edina. And backwashing, I think I mentioned this already, but it's a manual operation and it takes about 2 hours per backwash that you do. So there's 6 cells. Each cell has to be backwashed individually. The frequency of backwash is pretty dependent on the season. So on our shoulder seasons, the spring and the fall, we can get maybe a little bit longer run times. So maybe about 1 time per week. But in the summer when we have algae cooking, 2 times a week is good, but it's sometimes more than that. And the fish screen itself also needs to be, oops, I'm sorry about that, also needs to be cleaned. Just because we get algae, debris, filamentous algae and debris building up on it that effectively acts as a dam on the pump. So we have to go out, scrape it, sometimes more frequently than we have to do a backwash. Okay, so that's an orientation on the filtration system itself, sort of the engineered portion of it. This is sort of the outline of the project, the performance monitoring program that was funded by the Minnesota Stormwater Research Council. So this gives you a rundown of what we did. So between August of 22 through the end of last season, which was earlier, it was, I think, September or August, we collected 24 sample sets. And these are the parameters we looked for. So we had field parameters. So this is the example here. We have our YSI and our water samples from one of our overflows. And that's just collecting our field parameters, pH, oxidation reduction potential, that's ORP, temperature, specific conductance, and then separately we have a turbidimeter. And then lab samples we collected for total phosphorus, total dissolved phosphorus, ortho-P, TDS, total dissolved solids, total suspended solids, TSS, ammonia, total Kaldol nitrogen, TKN, and nitrate and nitrite. And then we did do some reduced frequency sampling, total alkalinity, and some metals. The primary purpose of these metals, so we have calcium, magnesium, those are our hardness parameters, right? And then we have iron and aluminum. We're looking at media integrity. And then just to orient to, I think we've already seen some of these pictures, but this is the effluent from the filtration system going up into Lake Cornelia here. We know that's a YSI in a jar. Here we're looking at, so this is our last sampling point. So this is just a small hatch that goes to the effluent. So it's a combined effluent sample that gets both the filtration, filtered effluent, plus any of the overflow. Okay, so first data graph here, this is just to give you a sense of what we see for flow. So the system I mentioned was started up, actually Erica mentioned, commissioned in July of 22. We started monitoring in August of 22. Since that time, we have pumped about 90 million gallons of water. And just under half of that has gone through the actual filtration cell. And so that gives you a sense of how much volume of water actually ends up going over the overflow from the anthracite, right? It's not all going through. And then the average flow range, so the pump, and I think I mentioned this already, somewhere around 400 GPM. And again, only about half of the flow is going through. The photos that we're showing here, I wanted to orient you to this earlier, but I didn't. We're looking down into the filter vault here. So that's looking down into the vault where the submersible pump is. And then the photo on the right-hand side, that's actually looking at the overflow from one of the filtration cells. And I just wanted to point out, because the flow meters are kind of interesting. So there is a little plastic weir structuring here. So the weir is just calibrated elevation to flow. And then on the left-hand side, you can see a little PVC pipe sticking out next to where the water is coming out. That actually has some bubble tubing coming out that's then going behind the weir, and it's at the bottom of the pipe. And it just sends out a little bubble once a second or so. And it's just measuring pressure, right? So it's measuring the elevation of that water in the pipe. And then we've calibrated it to flow. So then that's how we measure effluent flow. So 2023 is what we're looking at for flow rates on the graph. And this is the 2022, we weren't yet recording real-time flow data. And then in 2024, unfortunately, we still have the influent flow, but unfortunately the bubblers did not hold calibration. So it was like we would get good data for a few days and then they would be all wonky. So we would be seeing flows that looked like they were bigger than our influent, and it didn't make sense. So what we're looking at here is really the influent flow in blue from 2023. And then red is the total filtered effluent. So it's the sum of the green, orange, and blue lines, right? So that's our individual measurements coming out of the filtration cells. Highest recorded is from cell 3, so that's actually the middle one that has CC17. we'll talk about that one. CC17, because it's a coarse aggregate, and we all know we love ZVI, but it likes to rust and fuse over time. Because it's coarser, it maintained its hydraulic conductivity. So that's why we think that we got more flow through it relative to the other two that were granite sand. Okay, that's flow. Now looking at some field parameters. So just to walk through, so the x-axis is the same in both, but it's just month and year down here. And we're looking at pH and dissolved oxygen. And we have 2022 separated by winter, 2023 separated by winter, and then 2024. And the colors, we have kind of a purpley dark blue, green, teal, and orange. And what we're looking at, again, we're looking at pH here through the filtration cell, and we're looking at dissolved oxygen through the filtration cell. Few key things that I want to point out. pH, you notice this, 2023 again, we have our best record. We see this very quite high increase spike that we probably all know it's the algae working, right? They're sucking all the CO2 out of our water. So because we know how alkalinity and CO2 and pH works, pH goes up. And so we get this sort of temporary hump when the algae are really working. And actually we see it again in 2024, although it was a little bit delayed. And in 2022, because we only got 3 good data points, you can see the pH is still relatively high relative to where it is coming out of the filter. So I think there's a couple of explanations as to why, why does the pH come in so high and why is it moderated as it's coming out? Because it's CO2 driven, my guess is that it's probably just we're pumping and moving the water around and it's coming back into equilibrium with CO2 in the atmosphere. But the rusting and precipitation of iron, right, that process is pH dependent too. So there could be some buffering happening from the actual iron media. So that's pretty cool. Dissolved oxygen then on the bottom. So dissolved oxygen, that's giving us a sense of what the oxidation reduction potential of our system is. So I'm going to focus again on 2023 because we have a really nice record here, right here. And what we see, blue again is the influent, right? And the first thing I think that we notice is pretty constant. So 8 is, that's high, not quite at saturation, but high. And then once the algae start going, we see a bump in oxygen, right? Because they're photosynthesizing and spitting out all their oxygen. So we see a bump in oxygen. And then it flatlines again at somewhere around 7 or 8. What's coming out of the cells, we see a dip in the summer, right, down to 2. So maybe what we'd call suboxic, or if you're a biologist, anaerobic, just before anaerobic, because there's still some oxygen around. And, right, so 2 things, right? We have iron in the system, it's a reductant, it likes to consume oxygen. But because we see this strong seasonal trend, I think a better explanation is probably we have some microbial activity happening in the filter. Right? So it's consuming the oxygen, things warm up, they consume the oxygen, and as a result, we see it coming out. What I'm not showing here, and I wish I kept it, but between the influent and the aeration manhole, right? Because we're already coming in at pretty close to oxygen saturation, there's not a whole lot of difference, right? So we don't see a lot of difference in the oxygen that's coming in the influent water and then what's going over that standpipe that's then cascading down. So the big takeaway, though, that I want to point out, right, is phosphorus sorption is both ORP, oxidation reduction potential, dependent and pH dependent. And even though we see these wild swings, right, where we see high pH, and we might think, oh, that's really bad for phosphorus adsorption to iron. And we see low DO, again, because we could get reducing conditions for iron and then release the phosphorus that it's absorbed. Even though we've seen these things happen, we haven't seen a result in release of phosphorus from the filter. But I think monitoring these field parameters is still really important for the system. Okay, this figure is looking at, again, the x-axis is time and location. This time, instead of being grouped by date, we're grouped by location. And then on the y-axis, we're looking at phosphorus. And phosphorus is then fractionated. So the total bar height is total phosphorus. The lightest color is ortho-P. The middle sort of blue shaded color is dissolved phosphorus, but non-ortho dissolved phosphorus. And then the biggest bar is the darkest, is particulate P. So that's particulate bound phosphorus. That's anything that doesn't pass a 0.45 micron filter, right? And so I've got my main bullet points at the top here, right? 40 to 90% of the influent phosphorus is particulate phase. And the change, right? So in the summertime, I would say that's, right, when algae are going, that's 90%. And then when you look at the shoulder seasons, so I'm just gonna try to get my cursor here. There it is. So on these shoulder seasons, right, in the spring and the fall, that's where we see the distribution of our dissolved P and ortho P rise, right? But it's just because there's less total P around, right, or particulate P. So our system is seeing a lot of particulate P coming into it. And, you know, to me, right, there's a strong seasonal pattern, right? It's shoulder seasons are relatively low, somewhere around 50 ppb. And then in the summer, you know, somewhere around 100, 150 is more typical. And, you know, my best guess, right, is we have some internal loading, we have external loading of phosphorus. Algae are really good at sucking up phosphorus. So if it's there, they want it, right? So the rates of phosphorus coming in and the rate at which algae like to take it up, they just like to take it up. So we see it only as particulate primarily. Let's see. Yeah, and the other thing I wanted to point out here is the dissolved non-ortho P, right? So it's like reactive P, right? But we didn't fractionate it anymore, right? So that's primarily organic bound phosphorus, but it's in things like nucleic acids or more complex organic matter. So if it's in a simple macromolecule like a nucleic acid or a phospholipid, like those things are readily available. But if it's in something more like DOM that's like needs to be biologically degraded before an algae can take hold of it, right? That's less reactive. So we didn't fractionate it any more than we just have some organic bound P, dissolved organic bound P. Okay, so I know I kind of skipped over it on the last slide because I think it's really hard to see of, you know, what did actually happen going through the filter cell? Because if you squint, you know, you look at the influent and you're like, oh, I guess it's a little lower than the effluents. This, I'm hoping kind of has that story a little bit more clearly. So rather than being grouped by location and then date, now we're grouping by date and then location. So the darkest bar is the influent, and then we have post-anthracite. So that's after we go through the pre-filtration to remove suspended material. Then as you go down in the shades, right, that's the effluent from each of the parallel reactive media cells. And so the biggest thing that I think probably all of you see right away is the biggest drop happens through our anthracite. And it should come as no surprise, right? Because I just showed you that most of our phosphorus is particulate. So a lot of our phosphorus is getting bound up in the anthracite cell, which I don't think I mentioned it, but it's pertinent, is when we do a backwash, right? That backwash water has all the solids still in it, goes back to swimming pool pond. So then we have a phosphorus load that is ultimately sediment material. So I think that's the main takeaway that I wanted to point out here. The other one too that, I don't know, maybe I shouldn't draw your eye to it, but I like to point it out because this was kind of our learnings that we had in the first part of our monitoring program. So you see that the second bar is higher than the influent bar. And I already mentioned how we collected post-anthracite was in a standpipe. So it's this 12-inch pipe that goes down to the bottom of the media. You know, that water, once it's in that pipe, can go nowhere. So we had not really flushed that pipe out before we collected a sample, right? And so you can imagine leaves and debris getting stuck in it. And so we just didn't do a very good job of flushing it out before we actually collected the sample. So once we figured that out, we brought a submersible pump with us and we pumped it out every time before we collected that sample, and we got more results that we would expect to see and not stagnant water sitting in a 12-inch pipe. Okay, this is sort of the main takeaway slide for phosphorus removal efficiencies, right? So if we look, and these are just putting numbers to the charts you've already seen, right? So, and these are median numbers, so they're typical, right, average. So total phosphorus, 23% removal through cell 1, so that's anthracite. And then another 12 to 15% removal through our absorption media. The lower media through cell 2, which I haven't gotten to yet, this iron fusing issue, we'll talk about it in a minute, but the iron fusing in cell 2, so that's the granite sand with ZVI, that one we saw a lot of wall effects, right? So it fused, the water couldn't go through it, so it's coming up and around and not getting very good removal. Still seeing the same flow go through it, like it can still push the same flow as we see in cell 234, the last one that also has granite sand, but we see less removal because, yeah, it's got all effects. And then you can see the numbers for TDP. So there's almost no removal of total dissolved phosphorus or ortho-P through anthracite. There is a little bit of removal of the total dissolved phosphorus fraction through anthracite, but not a lot. And then you can see the numbers there for percent removal, 16 to 21% through the reactive cells, and 25 to 33% removal of ortho-P through cells 2, 3, and 4. And then just to clarify too, when we're looking at this, because I mentioned that the combined effluent has overflow, this is actually a computed number. So this is just total filtered, so it's doing a flow-weighted composite of cells 2, 3, 4. So rather than having any component from the overflow that's not treated, that is just accounting for what's treated. So the main takeaway here is, the cell somewhere around 30 to 40% total phosphorus removal. Okay. Operational troubleshooting. Are we giving 15 minutes for questions, 10 minutes for questions? Okay, great. Okay, so operational troubleshooting. So a few things that were challenging. I've already talked about the backwashing. So the backwash cell was broken into 6 different cells so that we could use a forward flow pump in order to do a backwash. But as it turns out, some of our calculations were maybe a little bit off in the fact that we didn't account for the colder water coming in, right? So the backwash that we were doing wasn't as effective as it should be. And so we were actually, and Ross, I know your team saw these, right? We were getting mud balls in the anthracite. And mud balls just form when you're not removing suspended solids from the anthracite, right? They just get stuck there and they just build up over time. And then as a result, we would do a backwash cycle. You wouldn't get the forward flow performance that you'd want back from it. Upflow filter cells, I've already mentioned this a couple of times. The 2 that have ZVI in them, we noticed fusing. And actually this nice picture down here, this is my attempt by hand of trying to break it up. So it's not the whole bed because there was a lot of work and not a lot of space in the cell to actually move the material around, but we did make a couple of attempts to try to break up that media. And that, of course, causes preferential flow. And then air entrapment. I'll talk about this in a couple of slides because I did do a couple of diagrams to walk through what I mean by air entrapment. Basically, what was happening is air was getting trapped in the underdrain pipes between anthracite and the reactive media. So it looked like the anthracite was still plugged, but it was just really air that was stuck in it. And you can actually see the water, it was like boiling when it was going through the anthracite at first. And just to, tell you too, so this is actually doing a backwash cycle right here. So all these are the hatches that we have open that are opening and closing the backwash pipes. And then this is a valve key here in the foreground that we've got the backwash pipe open and going to swimming pool pump. Okay, so talked about the media fusing and the backwashing. Backwashing, plan here is to get a higher capacity pump, something that will give us more oomph when we're doing a backwash cycle. I think we need something on the order of 700 GPM. So the engineering challenge right now is really to figure out where can we get that flow to make that happen. And I mentioned this already, key design parameter here, and this I think is pertinent if we're thinking about TSS or particulate phosphorus removal in a filtration system like this. We can't make assumptions in terms of maybe summertime high temperatures, right, to get the same backwashing fluidity, right? So when we're talking about backwashing, maybe I did a poor job of explaining this, but right, the temperature of the water matters because the viscosity of the water changes with temperature. And the colder it is, the more gel-like it is, and the less ability it has to raise and fluidize the bed. So if you make an assumption that your temperature is warmer than it actually is, you're not going to get the same oomph that if it was actually warmer. So we assumed warmer water temperature than we actually had. Media fusing. So I've got a couple of pictures down here. This is just showing, again, our attempts to try to do this activity by hand. Again, this is a 2-foot media depth, and this is looking at cell 2. So this is the granite sand with ZVI mixed with it. It was fused the whole way through, right? The top wasn't just loose and the bottom was fused, right? It was the whole thing was fused. And so this is just showing, right, we were using, just to point it out, this sort of electric hand chisel. And That's basically just a mini jackhammer. It just oscillates back and forth to try to break this stuff up, because just using a shovel or a hand pick, it was a lot of effort. So we did as much as we could by hand as a research team. But you can see, right, here's our challenge is we had nowhere to put the media in here because we've got these vertical walls all around us. So the plan here is that we've got to bring in some heavier equipment, right? We've got to actually get something to scoop out some of the media and then break maybe the rest of it up by hand, use a vector truck. Again, that hasn't been decided either. Okay, so the air entrapment question. So this is just a figure just to show, right, when we're operating the system, and this was at the beginning. The convention is, hey, we need to allow ZVI to dry out so that it can oxidize and reform new iron oxides and not get reduced. What we were finding, so the way we designed this thing is we designed it so it would be on for 12 hours, off for 12 hours. And then when it was off, we just had this passive weep drain. So I didn't draw this in the first diagram we looked at, but there's just this weep drain that goes just to the effluent pipe that gravity drains to Cornelia. That just allows the media to dry out over time, right? And so over those 12 hours, you would basically get media now that is dry, except for perhaps whatever is below this weep drain elevation, invert elevation. So this is when air can get into the under drain system, right? We've dried it all out, it's drained. Next slide. So then the air entrapment, right? So then we go to forward flow, 12 hours have passed, now it's morning again, we're pulling water. What we see is basically a column of water that just wants to sit on top of the anthracite. And my feeble attempts at kind of illustrating this, right? We've got air stuck in that pipe with nowhere to go. So the fix for something like this, right? In water treatment and pipes, you put air release valves, right? You put them all over the place. Anywhere where you've got a low point, you want to put an air release valve so you don't get air stuck in your pipe. That's the fix. It's not quite as simple as this. And I couldn't figure out a great way to show it on the diagram, but that's the goal, is to put an air release valve on this thing. So the air has somewhere to go other than back up through the media. So our solution for now has just been to try to run this thing as frequently as we can, right? Don't give it 12 hours to drain and dry out. Okay, cost estimates. I'll go through this so that we have a little time here for questions. So basically what we're trying to show here is we're going down construction, annual maintenance, annual operating costs, putting all those things together over a 30-year period with a 3% interest rate comes to about $107,000 per year. If you want to put that on a flow basis, that's about $4.50 per 1,000 gallons treated. This just gives you a sense of what we're including in all these things. So construction of the system, about $1.5 million. Annual maintenance, right? That's accounting for things like pump maintenance, attrition, like replacement of media due to attrition, right? Backwashing, you just lose a little bit of anthracite every time. And then annual operating. So that's really an operator going out there doing backwashes, cleaning the fish screens. Okay. So then the cost benefit, right? And I think I was here like a little less than a year ago, I think, when we were doing the annual meeting, but these are similar numbers to what I presented then. We're looking at somewhere around $9,500 per pound over that 30-year period, right? So that's just dividing our annualized cost by our annual. Again, we have 2023 as our best records, but we removed a little over 11 pounds of phosphorus. So it's just a simple division. We talked about a couple of the improvements that we're talking about. We're talking about a couple of improvements already. The bigger pump to do a more effective backwash and breaking up the fused media. With those two improvements, we're hoping that we can get 70% more through, more water through, equating to, instead of 11 pounds per year, more like 19 pounds per year, so that we hope to bring our future cost benefit down to somewhere between $5,000 and $6,000 per pound. Okay.
Thanks, Andy. And I think we want to wrap up on, beyond the research value of this filtration vault, which is also designed so we can swap out media and try other media types and put in media that's optimized for phosphorus removal. This is also a great demonstration site. The filtration vault is in a heavily used park. And so we've done multiple tours to show the filtration vault, explain how it's used. And we also have an interpretive sign out there so park visitors can understand what they're seeing, learn more about water quality and the type of projects that we do to improve water quality. And the one thing I want to point out about this sign is a fun thing that we did is it actually has a touch and feel component to it, which you can't see in this graphic, but we took a little bit of each type of filter media and it's glued onto the sign. So you can actually see what each of the filter media looks like and touch it as well. So I think that's a neat component of this educational sign. And with that, I just want to say thank you. And I especially want to give a shout out to the city of Edina. They are the folks that are operating this system for the Watershed District. And of course, this project went in partnership with them. And so they have been critical in the operations and troubleshooting of some of the things that we need to improve and move forward with.
All right, round of applause for Erica and Andy. All right, we just have like a few minutes here before we have to break for lunch, but we're going to be alternating questions between in-person and online. So first one we'll take in person. You can just raise your hand and I'll bring you the mic.
Thank you. You talked about the system runs about 400 gallons a minute with the pump. Mm-hmm. Is that just a fixed rate when it's on, yeah. It's full on?
It's on and off. So yeah, so thinking about the future and a bigger pump, right? I put it in there, but I didn't say it. Have a VFD, right? So you could, yeah, optimize.
Exactly what I was thinking.
All right, online question?
Our first online question for today is, how do the observed P reductions compare to design anticipated reductions?
That's a wonderful question. I wish I had the numbers. The actual were definitely lower than the design, but I don't have the design numbers stuck in my head. But if whoever asked that wants to email me, I can dig them up if they're interested.
Thank you. I'm really curious about the backwash.
Yeah.
So if I understand this correctly,
yep.
You're getting mostly particulate
yep.
in the anthracite.
That's right.
And then you're backwashing it back to swimming pool pond.
Yep.
So is everything removed in the particulate in the anthracite simply recycled back into swimming pool
it's
pond?
It's still in the system, that's right.
So we really can't take credit for saying it's removed.
Other than the fact that now it's dead algae that can sink to the bottom.
So you killed the algae. Okay. One other question, if I may, quick. Thank you. Why not automate the backwash? I mean, we do that all the time on other types of filters.
Yeah.
You could do it much more often.
Yeah.
So you wouldn't have these periods of time where the thing is just plugged up and bypassing.
Yeah, no, before you hand it back, Randy, I did want to ask you, so when you're talking about, we do this all the time on filters. Context is drinking water, wastewater?
No, I used to, in an earlier lifetime, I designed swimming pools and aquatic centers.
Okay.
And so we ran sand filters.
Yes.
And we backwashed them. I've heard stories about irrigation systems, stormwater reuse irrigation systems in Florida, where they have sand filtration in place.
Sure.
And they're backwashing at 15-minute intervals.
Right. Yep. Yep. So some context, right? So yeah, so when you're in a drinking water treatment plant situation, right, you're backwashing really frequently. And like as we get to higher filtration, UF, you're exactly right. It's like every 5 minutes these things are getting backwashed because they get plugged up so quickly, right? So think about that though in our setting, right? Like, so I appreciate that, your irrigation system, it's a small volume of water, you've got a little canister, right, that you've got to backwash. Not a big deal. Here, you've got to now figure out, you've got to put in all these valves that either have to be air actuated or electrically actuated. They're very expensive. You now, if you do air actuation, which is maybe a little better, right, you need a compressor, right? So there's just a whole lot of stuff. Now you've got to put a little building, right, so you can house all these things. So it becomes vastly more complicated, right? So I think when we're talking about this system, right, and going with the flavor of it's experimental, right, it's like, let's do this first step. Let's do it manual. Let's see how it works. So that's where we're at. I want to just mention too, because I think my answer to your first one was a little snide, right? The phosphorus removal, right? There's opportunity there, right? Like, no, but there's so much opportunity there, right? Like, because you're capturing it, you have that phosphorus. There's an opportunity. So, yep.
All right, question from online.
Do you know the contact time with the materials in the filters?
Yeah, so it varies, right? Because we can get different flows, but it's about 10 minutes.
The backwash outflow, it looked like from the example it was going overland, or was that piped straight to?
Yeah. No,
Living
yeah,
Pond?
I don't think I put a picture of the actual backwash coming out, but it's piped. It goes on. There's a
Okay.
street actually right there, so it's all underground.
What's the expected lifespan of the filtered media?
Unknown, but assumed to be somewhere on the order of 5 years.
Andy, I think Randy was definitely on the pulse here. When we designed this thing, I think we had in our minds an expectation that a lot more of the stormwater or surface water we'd be treating would be dissolved. And it really surprised me that, when you look at that phosphorus types graph, 90% for most of the year is particulate.
Right, when we're operating. That's
Yeah,
right.
and I think, when this, to frame that up for people, when you're at the end of the pipe and you're talking about stormwater, that is right after a storm, right? But when it hangs out in a pond or a lake for more than a day and it gets any sunlight on it, that dissolved phosphorus is immediately utilized.
It's sucked up.
Yeah,
Yep.
so one more back from this one is the graph I'm talking about. The blue bar, that's all algae. So when you start to go, you think you have an opportunity with taking, not storm by storm, but
Yes.
continual treatment.
Yep.
And if you're getting in any surface water that's of any appreciable size, starting to think about much more particulate design, I think is the key. If we were to know what we know now,
Right.
and roll again into that design process, that anthracite filter would be the majority of the space.
Yeah, that's right. And we mentioned it, Erica mentioned it when we started, right? Cited it here because swimming pool pond is right there, right? So you have a water source, but exactly what you just said. It's no longer fresh stormwater coming in. It's sat there for some residence time. And yeah, the algae take it up so quickly.
All right, looks like it's about time to break for lunch. So if you had questions online that weren't answered, we're going to send those to the presenters afterwards and send you a copy of the answers with a follow-up email. All right, welcome back to part 2 of the Minnesota Seminar Series. Again, I'm Maggie Karschnia. I'm the moderator today. So we're going to be giving the panel some questions just to initially kick us off, and then we'll be taking questions from the audience. So those of you joining us online, again, please put your questions into the Q&A, upvote it if you like the question. And with that, we'll get ourselves started here. So we've all faced these challenges of this growing population in these growing urban areas and trying to fit these water quality practices into these tight urban landscapes. So this discussion is going to be not only on these wonderful media filtration devices that we're now innovatively coming up with, it's also going to focus on other things. We've seen a lot more tree trenches over the years. We've seen a lot more underground filtration systems. We've seen a lot of different creative ways to address this problem of these tight urban spaces. So we've got a good panel for you today, a lot of diverse experience in this group. We're going to have a really good discussion, and I'm really excited for it. So we're going to start us off with just some introductions and a few questions for our 3 folks who are joining us on this panel discussion. We're going to start off with Nancy Stowe. So Nancy is a projects and planning director at Mississippi Watershed Management Organization. You might know Nancy like I do from maybe one of her previous roles. I worked with her a little bit when she was at Houston Engineering. She's also been at WSB. I think you were on the Clean Water Action, working for them too. Yeah. Oh yeah. Yeah. all of these things. Like she has a vast, great experience to offer. And so Nancy, from your perspective and experience, like how do you relate to this topic?
Yeah, I can't speak much to anthracites, but I can, speak to the need of high volume, low footprint innovations. The MWMO covers 40 square miles of urban area, almost mostly built out with a lot of impervious area that flows right, into the pipes and then directly into the river with not very much space at all to build projects for pollutants. So love the topic.
Our next panelist is Kyle Axtell. He is a watershed project manager at the South Washington Watershed District. Kyle's had a 20-year career working mostly at watershed organizations. He is also on the Minnesota Stormwater Research Council, and we thank him for his contribution to that. That's what makes this and all of our stormwater program possible. So Kyle, same question for you. From your perspective and experience, how do you relate to this topic?
Thanks, Maggie. Good to be here with everyone. Like you said, I've spent most of my career working in watershed management, really trying to work as a liaison, through the watershed district, working with cities, counties, other partners to find ways to make improvements to water quality, flood control projects, and particularly in the Twin Cities metro area, other metropolitan areas fully built out, building out. Space is tight, and so this is a topic that is like every day, as we're trying to develop new projects and work on things. So very interested and excited to hear about the project we just heard about. So.
All right, thanks, Kyle. Our next panelist is Ryan Johnson. He is the environmental manager at the city of Roseville. Now, if you're not familiar, Roseville is a step 5 green city, and I believe that Ryan is a big part of why that happened. So they're doing incredible things with sustainability. You're always innovating and doing new things over in Roseville. And so same question for you, Ryan. From your perspective and experience, how do you relate to this topic?
Thank you, Maggie. And yeah, this is an exciting topic. This is what we do every day in Roseville. I do every day in Roseville. The city is a first-ring suburb, built mostly 50s, 60s. Stormwater management, wasn't a thing. We found old reports that says, the stormwater system was built for a 5-year rain event, and this was back in like 1962. So, we have very little resiliency. We have very little open space, just given how dense Roseville is now with all the impervious. So, it's like we do look at doing everything in tight spaces. I mean, our projects either go under our roadways when we redo the streets. We work with a lot of great partners with our watershed districts, looking for more innovative ways on like how do we move water from a surface water to something where we can filter, just because, we went through years of droughts where we have like these sand benches around things and, we're not getting a lot of filtering that way. So, what other things can we do within the city to really, improve water quality that way? So, so we rely a lot on our partners, and we just love coming to these series just to learn more about what we can do within the city itself too.
Great. Thanks, Ryan. All right, so the first question for all of you, feel free to answer whoever. We just talked about how the population is growing. We have tighter and tighter urban spaces. What are the biggest barriers you face when trying to implement water quality practices in these tight, urban, fully built out environments?
I can start, yeah. I mean, I think space is kind of the biggest barrier in of itself. I see it in multiple ways. Properties are smaller in the urban areas, so developers have a lot harder time meeting the stormwater requirements. Urban areas also lack space to build regional facilities. I find that a lot of our areas that we find to build projects, they're so small they don't have much slope, so it really complicates design to try to avoid the tailwater effects. Our member cities, they also all require treatment of the runoff for road reconstruction now, right? So, ultimately we want to put that green infrastructure along the side of the roads, but we have a lot of really tight corridors where it doesn't work. So that's a big challenge for us. And one other thing is like, we also have a lot of vertical barriers, right? We have a lot of urban fill. We can't really rely on circle soil information. We have utilities all over and you can't always move them. We have trouble predicting seasonal high water level because it tends to be erratic if there's a lot of various fill around. And also, since a lot of our stormwater is coming in deep underground in pipes, it's hard to bring that to the surface. We have to go underground and it gets really expensive. So that's kind of like some of our ultra urban challenges. So anybody else?
Yeah, that's one of the things I think about is working with existing infrastructure. As you mentioned, like the storm pipes, you know, if we're gonna try and retrofit a project in, you know, what's already there, you know, you say you've got a budget to build your project, but if you can't, you know, some of those things where your inverts are set coming in and out, you know, to try and move that or modify existing systems can be very challenging. I think about like where I work now and down in the southern end of Washington County, bedrock is a major, you know, limiting factor right along the Mississippi River over on the St. Croix. You know, that's not limited just to our area, of course, but, you know, so that now you get into cost can become a barrier. Just because you've got rock excavation that you might not have if you're up on the Anoka sand plain, right? So the other thing that comes to mind is even just, you know, maybe like political willingness or boldness. You know, a lot of our partners look to the Watershed District to be, you know, that entity that can go out and push the envelope and try new things, because maybe it's a little easier for us politically to do that, where cities maybe are under a little more of a, you know, focusing lens from constituents, for better or worse. But, you know, we work with our partners, and that's one of our goals as an entity, is to try and serve that role where we can.
Yeah, and to expand on that, I know obviously cost is big for a city. It's like we have to break up a road to redo the project. We do what, you know, Kyle just mentioned, where it's like we're trying to utilize existing infrastructure, modify it so we can get some kind of infiltration, some filtration, and with the variability of soils and what we're on top of, contamination too, it's like it adds up very quick. And the other thing that we really, I don't want to say we struggle with it, but one thing that we're very cognizant of is just timing. We have to plan out a lot of our projects just because of the cost component to make these modifications under the ground. Once we start looking at timing, you know, it's like we kind of have our 5-year, you know, CIP built out. And if we do get this other project that comes up that's, you know, a little bit more opportunistic, maybe it's a partner project with a watershed district, you know, it's like we have to kind of, you know, work backwards from that a little bit just to, you know, if we shift funding from one of our other projects to this partner project, because maybe it's a little bit more regional, maybe we get a little bit more benefit. It's like, how do we rebuild maybe back our stormwater infrastructure, like under our road that we were planning to do with our pavement management project. So, because yeah, it's like once we start looking at spending 500,000 plus on the stormwater infrastructure just under our road, you know, that can take up a third of our entire stormwater budget just for projects for a year. So it's like the timing component of this is something that we have to watch for a lot. Just we want to make sure everything goes in. We want to make sure that we have good water quality. We have less rate, and yeah, it ends up being a little bit of a balancing act once we're in construction. And because yeah, once you start breaking up a road, everything changes after that. Just with, you know, what you actually find, you can plan for it, but once the excavator starts going, that's when you really kind of form fit a lot of things.
And I would agree with everything that's been said. I think it's really around what's the acceptable level of cost benefit. And if the cost benefit is high, are there other stacked benefits that maybe make that high cost more attractive? I would also say, you know, it's where do you have available land for these projects? When we're typically looking for project locations, we try and start on public land, because we typically have better success partnering with our public entities like our cities. But, you know, that takes a lot of time as well, as finding those partners who are willing to move forward with projects. So time and resources.
Go for it.
You have anything to add?
No, I was just going to say from like the technical side, I'm coming at it from an engineer and not from the public sector side. And thinking about, our specific system, it's a big design challenge to fit that system in the space and do all the things that we want, right? Like we want to capture the solids, we want to do automated backwash. The engineering takes a lot of time, and these are, we're going to a space that's less, what we're used to with stormwater infrastructure and more what it looks like for water and wastewater. And that's hard. It takes a lot of time. It takes a lot of manpower to make it work. So.
All right, we heard a lot about the challenges. Let's talk about opportunities. So I would love to hear if any of you have proactively explored and prioritized unconventional spaces for best management practices in these tight urban settings, whether that be a parking lot, maybe a partner property, could be any of those things. What have you experienced? What have you done that's been really innovative and helpful?
Well, I can start off. Basically in Roseville, it's like I have kind of my dream list of sites where if anything ever happens, redevelopment, they sell, it's like we have, at least kind of the high level plan of like what we could do there. And that's, something, it's like going under our roads right now or under our parking lots is, kind of standard. So it's like, now it's looking at, it's like if we partner with a church, they have some green space. It's like, what can we do with the green space where maybe they can, they can also get some benefit too, other than just the water quality side. Roseville has stormwater requirements. So if we have stormwater requirements, can we work with them to build in some benefit where they can get some of the credits where, maybe we do the project. If they ever want to redo their parking lot or expand on their building, we already have that kind of built into that. So we tried to be a little bit forward thinking with that just because, yeah, again, it's like we don't have a ton of extra space. It's like, we have all of our parks kind of identified for, where we might be able to like flood a field, where we can go under a field, just where groundwater isn't going to be an issue. So, it's like we have little nooks and crannies. We did a project with Rice Creek in the past where, it's like we pump water out of Oasis, similar to what Edina did, where it's like we're taking the water out, we're running it through iron enhanced sand filters and then putting it back into Ramsey County Ditch 4. So it's like, and these are all tight spaces in between like a pathway and the ditch and the sidewalk and the road. So it's like we have areas all over the city that we are looking for that type of opportunity because that's what we have to work with. So.
Yeah, I would think, and, in my past experience, we've done, both when I was at Rice Creek Watershed District, also now at South Washington, we've tried to do a lot of work to actually prioritize and plan for that. So whether that's, working with the Conservation District or a consulting engineer, someone to do kind of a sub-watershed analysis, some kind of high-level concept and feasibility work, looking for, proactively looking for those project spaces, what expected benefits we might be able to get out of that. Those are great ways to set your organization up for, both future work, also, good opportunity to use that to find grant funds that might be available to help move a project forward. Currently in Woodbury, where we just completed a similar effort around Markgraff's Lake. We're doing another one on Colby Lake. Those are going to get worked into our new watershed plan. That's going to drive our capital improvement planning in that area of the watershed for the next 10 years. And so it's, if you don't put in that work on the front end, then you're completely opportunistic. And that's helpful. Some things pop up you didn't think about, some opportunities, but you've got to have that groundwork laid, I think, to be able to plan for those, tight spots.
I would agree with that, and I think that plays off of what Ryan said earlier, is that timing is so important, is you have to be planning far in advance. And so one of the things we've been trying to do more proactively is meet with our cities, meet with the county, understand what roads projects they have coming up and how it might fit into our timeline. And as we move in, we have our next 10-year water management plan we're working on. How can we then build those conversations and that planning into our projects as well?
Even to piggyback again too, and getting that planning in place, like for instance, our Markgraff's Lake, City of Woodbury is here in the room today. We got that work done, we got the planning done, and then they've got a road project going on around Markgraf's Lake. We were able to quickly pivot and get, it's just a CDS unit that wouldn't have otherwise been added to their road project, but we've got this, hydrodynamic separator that is gonna benefit Markgraf's Lake. We were able to boom, get it added to the city project, the Watershed District's paying for it, and it's gonna get done. And had we not done that planning effort to know that that was a project that was, had a good enough cost benefit analysis that it's not the highest ranked one we have there, but it's a good one to do, we were able to get that done. So the partnership is important too.
Yeah, I was just going to say, we don't necessarily prioritize unconventional spaces, and we try to look at cost benefit throughout, but we find ourselves in those spaces a lot, and doing what we can there. I think we end up moving to hydrodynamic separators and modular wetlands and whatnot a lot, but we certainly try to target parking lots, especially closer to the river, that don't have any downstream BMPs. Having a bit of trouble, the MPCA is recommending not infiltrating over karst areas within 50 feet of the surface. And there's a lot of large parking lots in Minneapolis over karst. And when you're working with a church or a school, you're really trying to get that infiltration, because that's the most cost-effective way to remove the pollutants. And you don't want to leave these parking lots either, right? So you're trying to do infiltration, but now that we're looking at if it's over karst, if moving to filtration is very difficult cost-wise, right? Because then you have to have drain tile, it has to be connected to the city storm sewer, and the last estimate we had was like $80,000 or something, right? That really is a huge cost barrier. So I'm sending out to the world, we're looking for a really good geotech to tell us how much can we put. Is it 0? Can we do a ½ acre of impervious? Does it matter how deep the karst is below it? Because right now the guidelines, what I can tell, are really broad. So we don't want to create a sinkhole. We also want to clean these parking lots. So I'm excited for more research on that topic.
All right, so I have a question for you that I would love to hear the answer to. How might you use the research results from this Rosland Park filter project that we just heard about? How would you use that to change your approach to planning for and designing future filter systems? And Erica and Andy, I would also love to hear your answer on this too.
I'll jump in. One of the things that I love about this project is its ability to be used for research for filtration different filtration medias. Obviously, they're already trying a few out, but as we work more into tight spaces, I'm seeing this bigger trend toward active management, pumps, other systems that will automatically draw down ponds ahead of storms. Filtration medias are a big part of that. As we continue to do more research, the Stormwater Research Council's been focusing on that. So there's a lot going on, but having a system like this in place, or if there can be others to do that field research in the field as opposed to in the lab, I think is incredibly valuable for all of us who are implementing these things in real life, I'll say. But so that's one of the things I love about it the most.
Yeah, it's a fascinating project. It's one of those where, again, in my city, it's like we have iron enhanced sand, we have a few projects of those, we have a spent lime filter. So it's like we've been working with the watersheds primarily to kind of expand those and to do, some of the research, because it's like they are grabbing some samples after at the effluent of those. But yeah, it's just like I do love the idea of having multiple medias where we can test a lot of these all at once. I know, it's runoff is runoff, and, it'd be interesting to see if Roseville's water is cleaner than Edina's. I'm guessing it is. Ross Ross is in the room. No, but it's fascinating, and I love being involved in this role, with partners like all of these, just because, we all care, we're all trying to look for these types of answers on what media is going to get us the best effect, how can we really, take some unconventional approaches like the pumps, like, you know, being able to draw down ponds before. You know, in one of our projects in Capital Regions area, it's like, you know, there's actually a couple of wells where it's like Capital Region tests for viruses. It's, you know, so it's like, there's a lot of great work going into it. And yeah, it's just, you know, coming up with these great ideas and then implementing them in Roseville. I mean, it would be fantastic just to, I mean, it's like, I love the research side. I try to work with the U of M as much as I can and everyone else, because, you know, it's like, this is really going to start moving stormwater management forward, which, you know, it's an exciting time here just to be able to be involved and be, you know, hopefully one of the proponents to move a lot of this forward.
I think from my perspective, you know, we had really great support from our board installing this and knowing that it was an experimental filtration vault. And so I think, you know, we have some operational challenges that we're working through, but I think the exciting thing is that we can continue to experiment with the filtration vault and learn and share those results out to the community. I think as we think through what we've learned from the vault and understanding better the operations, you know, I think that this type of system, if we were to install it again, you know, we'd want to really think about what the purposes are, look at the cost benefit, look at the sites too. Like, do we have a really high priority water body that we have used other management practices maybe, and we need that extra oomph? You would certainly want to think about operations and maintenance and be able to access the system for operations and maintenance. Or, you know, maybe it's a site that there is limited space for other types of best management practices too. So, you know, I think it's been a really great learning opportunity, and it will continue to be in the future.
We'll certainly continue to follow and hopefully get the upgraded or updated graphs every year, and love to hear results of anybody else's experimental. We've done just a bit on projects comparing biochar and regular sand, and don't have incredibly conclusive results due to a little bit of operational issues like tailwater and whatnot. So thanks for that. Applaud 9 Mile for investing in innovation, and a plug out that MWMO and probably South Washington, part of our role is to support innovation. So come to us with great ideas that we'll include in our feasibility studies.
And I'll just add on to this from the engineering perspective, right? Thinking about this project, you know, we've already touched on some of the things like what we would do differently or what we would do better next time. But, you know, just going higher level, right? The concept of being an engineer and like taking that step and like, let's do this, right? Like, it's new. So like constructability is like a big deal. Like, is this something that we can demonstrate in the lab, but can we also demonstrate it on the full scale? So, you know, from my perspective, you know, I come at this as like, I don't know, less of an engineer, more of like a researcher. So like, I really like this type of work, right? Where you're doing something and you're, I don't know, testing it out for not the first time. Like, it's not the first system like this in the world, but you know, you're doing something that's maybe a little bit unconventional. So I just think, you know, having the support of, you know, whatever entity it might be to do that, and like to know it's might not work perfectly, but like, let's learn about it. Like, to me, that's, I don't know, the most valuable thing to take away.
May I just one more? I also really appreciate you guys talked a lot about the maintenance, and we're trying to really start collecting more data on the actual true cost and effort of maintenance so that we can advise our grantees much better. We're starting to do an inventory of a lot of our old projects and realize, or starting to get a handle on what have been the challenges, and a lot of times that's been underestimated. So I'd love to, if everybody could start collectively trying to keep track of maintenance efforts, create a nice database someday.
All right. We're going to open it up at this point to questions from the audience. So those of you online, you know, make sure you upvote the ones that you want to hear from, and anybody in the room, just raise your hand and I'll bring you the mic. We'll start with the first. Do we have one online, Levi?
It's also connected to cost benefit and maintenance, but people are interested in knowing how much staff time is devoted annually to operating this system, and how does the cost per pound of phosphorus removal compare to other types of stormwater BMPs?
Can we actually, Ross is in the room and he's with the city of Edina, so I would maybe ask if we could pass the microphone over to Ross to help answer that question since they're operating it.
Thanks. Ross Bittner from Off Camera. So your numbers that we're estimating in terms of a total dollar, I thought did a really good job of kind of giving us our all-in operations and maintenance costs. But if I wanted to break that $19,000 or $20,000 per year down, the major headline items are obviously labor for the backwashes is number one. And then we also have a variety of equipment that support that operation where we're depreciating that equipment. We have the system itself and its depreciation, which I think are all in the capital side of the game, right? And then electricity is a cost here. Yeah, it's majority staff time. So when you think about the opportunities for the operation, when we're thinking improvements, the way we can get those run times longer by really getting that backwash process is going to be key. So I like the idea that we could make this thing twice as effective now. And now that it's in place and we've already ate the capital costs, this might be part of the sunk cost fallacy, but it might be the most effective thing we can do is keep the thing running. So after you've paid it, you can kind of reassess the cost benefit. Did I miss anything, team?
So, Ross, I would add on to that too, and something that it struck me. They asked about the how does it compare to other things. I saw the numbers. It was $9,000 or something per pound. I think it's almost not to me very relevant because of the experimental factor of it. I think the value is in what we're going to learn, not necessarily. So that's something to maybe take to your political bodies or your governing boards. It's not always about that final dollar, and so many people like to think it is. It's also in a very urban setting, so there's different ranges of costs that you might see that, I'm looking at projects, if it's not 5 digits, like we're probably go, in terms of dollars per pound of phosphorus you might remove on a project, more rural areas, or if you have larger, more open space, don't have the tight space constraint, you can see projects that very easily can get down towards, $1,000 a pound or less. Nothing will beat street sweeping, plug for street sweeping. But yeah, so just thoughts on that.
Yeah, and I guess just to expand a little bit where it's, for any project in Roseville, it's like a majority of our cost ends up being the staff time, the long-term maintenance. We try to get these as, to be able to get maintained as quickly as possible, whether it's header rows or, CDS chambers in front or some kind of separator. We try to get it as streamlined as possible so we can build it into our just normal maintenance. With our little bit more high-tech, not quite to their level, but again, kind of the iron enhanced or the spent lime, it's like most of it at this point is just going out there, making sure it works, making sure water's flowing where it should be, and just, keeping it running. Because at this point, it's like for us, the pound per phosphorus removed is great. But again, it's like Roseville's kind of in the place where it's like, it's a little bit of an uphill battle to get to some of our TMDLs. So it's like, we're willing to put in projects that we think will work best in that space, just knowing that, we're going to take out whatever poundage we can. And again, it's like part of it is, the promotion of the project. We can get the project in the ground. These ones happen to be in parks. If we can promote it in a park, if, we can have other add-ons in there, like, this is what residents can do in their yards too. So it's nice to get that additional promotion in there just by having the project itself, which does draw some attention.
Yeah, I was going to add that too, right? We have that educational sign that, every time I was out there, there was at least one person would stop you and say, hey, what's this thing doing? What is, just to learn about what it is. Is it working? So just the public education piece, I think is super important, right? It's expensive, but it's part of it. So I think there's other things though, besides, just the public outreach that are unquantified when we just talk about phosphorus reduction, right? Public outreach is one. You might get co-contaminant removal, right? ZVI is actually really, really good for metals, right? So it's like, we didn't have wonderful metals data from our data set, but metals are a thing in stormwater, right? From wear and tear of cars and being right next to a highway. you know, there's other benefits to things like this that, you know, we just don't quantify with just phosphorus.
All right, thank you. Any questions from in the room?
So the filter used kind of reminds me of some like proprietary manufactured treatment devices out on the market. And I'm just curious, research component aside, was there a benefit to the design or the layout that maybe you wouldn't have gotten from a proprietary device? And then also maybe from the city and watershed district side, is there more or less willingness to utilize and permit these manufactured treatment devices based on this research?
I can start. So I don't have a ton of experience with manufactured devices, right? So everything that we put in this, like a civil engineer can construct the cells for you. Oh, I shouldn't say any civil engineer because I'm technically a civil engineer. I couldn't design it. But, you know, there's lots of people that could design it, right? I can tell you exactly where we got all the media. So if you wanted to go and build this thing, like you are more than welcome to. Like proprietary things, like I don't know, I kind of shy away from a little bit. So from my perspective, I don't know, I'm an engineer, so I like to construct it and build it myself. But I don't know, from your all perspective and using kind of more of the proprietary stuff, I'd be, yeah, interested here.
We see them a lot. We've been installing them quite a bit lately too, and they, you know, I think everything has its place, right? If I'm working down in Newport and St. Paul Park, right along the Mississippi River, bedrock is 2 inches below grade. You know, a lot of times we're just putting a hole in the rock, we're putting in some type of device in there just to get something. We can't infiltrate water down there. We can't do surface BMPs. The cities can't do it. So we're trying to work with them to get some kind of treatment that we can do at the ends of their storm outfalls to the river. And down there it happens, our main concern is TSS, sediment. It's, you know, that's the main concern in that part of the Mississippi River. So we'll try and get some phosphorus where we can, but we have a different goal. And so that's where, you know, those devices have a very strong place for us there.
From my side, honestly, it's, well, on the permitting side, and, you know, it's like, if anybody comes into Roseville and offers up to do one of those things on their development site, I will permit it gladly because that would be fascinating. Just because usually the stormwater costs, when we talk to them on the front end and like what they have to do, they, you know, they kind of do the eye roll at me and, you know, it's like, this is what we really have to treat. And it's like, yeah, it's kind of written out like that. So, so yeah, it's like if I would be all for, you know, permitting something like that, or at least working with smarter people than me to tell me if we should be permitting it. And, you know, just to make sure it does meet all of our rules, because it's like, it would be fascinating. When it does come to like proprietary, it's Roseville, we're all over the board. It's, you know, honestly, like Andy, I like building things. So if we can build something, you know, a little bit different, that's easier for us to maintain, that's great. A lot of the time, the proprietary items, you know, I've already kind of taken that into account. So, you know, it's like, so we use kind of across the gamut of like what we'll actually install. But, because yeah, it's like, we try to be as innovative as possible just because one, you know, we're in a good spot where we can do some of this, you know, some of this extra research with it, try something a little bit new. Again, it's like we have a lot of staff support and council support where it's like, you know, I can get by with doing something a little bit more outside of the box. As long as we have kind of a nice story for the end that this is what it's going to do, this is how it's going to make things better, you know, show the benefit for the city and for its residents, you know, that goes a long way with us. But yeah, honestly, in the end, it's like I'd try pretty much anything if it's shown that it can work, or at least if there's the idea that it can work.
I would take on to those two too, right? Like it's not a one like size fits all, right? Like there's lots of different sites, different needs. You know, for this one, right? You're talking about bedrock and drilling a hole and putting a canister or something in it. In ours, right? You know, the landscape architecture of the system mattered a lot, right? In terms of like fitting into the park landscape. So it's like, you know, would you do this everywhere? Probably not. But there's, you know, so from the standpoint of like, you have to be creative in terms of what you put where, but also having like a multiple barrier approach. Like I find it like you need lots of not lots, but you need more than one thing to tackle all these problems that we're, faced with, right? And water treatment is, what we're talking about here, but, in our case, we have this end of pipe treatment, but they're doing alum treatments, they're doing curly leaf pond treatments, right? It's not just one thing. Yes.
All right, let's go to a question online.
You mentioned a $850,000 grant that was used to fund the Rosland project. Do you know of any grant opportunities that we can mention to clients to help offset some of the costs associated with projects like this?
Claire can jump in. There's lots of grants. We received those 2 grants, one from Hennepin County. They have, an opportunity grant. And so we had received, I think, about $100,000 through that grant. And then we had a Board of Water and Soil Resources Clean Water Fund grant as well. But as for just listing off grants, I'm not going to be able to do that off the top of my head.
There's so many, and I think we're fortunate to be in the state of Minnesota that places a great emphasis both on the importance and also then to put the money behind it to fund innovative work in the stormwater field for the benefit of our citizens. That doesn't exist everywhere in this country. But yeah, to list would be, find a state agency, visit their websites, visit your locals. They're out there.
Yeah, I was going to say Watershed's, at least the MWMO, we also, in addition to building projects, we'll also provide grant funds for good designs that have good cost benefit numbers, et cetera.
Yeah, and if you're a city, just reach out to your watershed district and ask. Because they'll either give you cost share money or possibly, and they'll also say, we should apply through this too, because they are very up on all these other grants that you can get. So my first stop is always the watershed, and they've always been helpful to find, other than just their resources, how they can best leverage some of the state money involved too.
Yeah, so please talk to us early so we have time to apply for grants. So, good.
All right, we've reached the point where it's now time for our closing question. So this question will go to all of you, and we'll start with Nancy and work our way down. What are your key takeaways from today's seminar, and what lessons have you learned on this topic that you would like to share for the benefit of our audience?
I learned about different types of media that I had never heard of before, so I feel quite enlightened there. We'll certainly be looking at all those different options. I learned that we need to keep doing research, and research needs to keep getting funded. And we need to make sure this information is accessible in multiple forms, I think in high detail for scientists, on a practitioner level for engineers, for design, and then sometimes a little altered presentation for project or property owners or project owners and decision makers, a little higher level. Yeah, continued research, continued dissemination. Thank you.
I'm going to pivot a little bit, but one thing I think that I've taken away from this is the idea that there are all these barriers out there, and we've provided different examples. Just find ways to work through them and overcome them as you're developing projects. Work with your partners. I think that is critical. One thing that I wanted to get to today that we haven't, though, is the idea about trying to fit these things into tight spaces. Aesthetics can be an issue. We talked a little bit about that, I think, with your project. There's so many different considerations that can come into play. You're putting a project on a public park, for example. People they're going to care what it looks like. Don't overlook the opportunities that exist to involve public art into your projects. We've been making a very concerted effort to do that at our watershed district on some big capital projects that we've been working on, and it's been going very well. It's a nice way to engage with the public, get some additional interest in what's going on, and somebody might also learn something while they're there. So, and you can beautify the environment, right, as well, with some cool art. So don't discount that.
Yeah, can you provide an example of how you used art in one of your projects?
Several. How much time do we have? Recent projects in Woodbury, Hassenbank Park. We've got really 4 public art sculptural installations that have been installed there. Fortunately, our board was willing to make that investment into those installations. We're currently working on an alum treatment facility at Wilmey's Lake. We just hired an artist to do a big mural project on a screen wall that was there to kind of block the backside of like the giant control panels that run the pumps. It's just ugly green boxes, right? So screen wall was there, and it's like, well, we've got this giant 15 by 9 wall, like we better tag it before somebody else does, right? So, but we've got an artist we're working with on that, and that'll be unveiled later this year. So.
All right. I guess my key takeaway from all this is just my overall fascination of just again, just kind of the creativity and the research and everything that goes into, you know, making these newer, innovative BMPs, using all this new media, you know, and just really trying to, you know, get the creative spot, get it into an area where it can get used, it can get maintained, you know, because again, when we are looking at these tight spaces, you know, it's like we can usually get it tucked in there, but it's like, how do we maintain it? You know, what does that really mean for like, you know, the city staff who go out to do it a lot? So it's just like how much a lot of that is all coming together. And I very much appreciate, you know, all of you and Ross to do a project like this, because, you know, it's just going to help move all this forward again. And that's, you know, just kind of my big takeaway is just trying to find these practical solutions, make them kind of crazy, add all these different medias on it, find out what they can do. I would always like to do that. So it's hopefully Roseville can do it in the future. So we'll have to reach out, but yeah, the takeaway is just, you know, try it something new, find a good partner.
My takeaway is, I think, just the support for innovation and research. You know, when you put in these practices, there's some risk with doing so. And so I think just having that support for innovation and research really is important to get more of these things in the ground and help us as a community learn what's going to work as we continue to try and improve the health of our lakes and creeks. And then we had a question during break of, did we see one of the media as a winner? Like, did one like jump out to us as this is the one we want to use, or really good results? And I was going to ask Andy to maybe answer that question as part of his wrap up.
Sure. Yeah, no, thanks. So when we applied to the Minnesota Stormwater Research Council grant, like that was the outcome that we were expecting. Like, we're going to test these media in parallel. We're going to see which one does best. And maybe it didn't come out in the data, but they really, like, percent removals were about the same, right? So where it really comes out is, we've already heard from Ross, right? Like, it comes out in the labor, like how much it takes to maintain this thing. And so from that standpoint, like, you know, the anthracite, we've already talked about that a lot, right? The backwashing is kind of a pain. But the other ones that have fused, like, we have to go out there now with excavator or something to like break it up. And it's in a concrete small basin. So it's, you know, it's things like that where it's like, yeah, it's not a conventional job. It's not a fun job. It has to be done, but it's like, yeah, it's things more like that, the operation side that, you know, it's probably going to be our bigger determining factor than, you know, this one removed, you know, 1 pound more phosphorus, right? And then Maggie, to your question about, you know, the takeaway, and like, I think mine is kind of maybe just copying everybody, but, you know, it takes a village, right? And I said that at the beginning, right, of our project, but like thinking more broadly, right? Like, it takes a village to do a project like this. You know, not even just the engineers, like the watersheds, the cities, right? The public, right? They get a say in terms of how this thing looks. So it's like, you know, just working together and making it work, like, is the most important, I think.
All right, thank you. Well, it looks like our time's up, but please help me in thanking all of our panelists with a round of applause. So all of the questions that you had online that weren't answered, we are going to follow up with that email, and hopefully everybody here will help answer those questions for you. We hope to see you at the May 15th seminar series coming up here in just a couple of weeks. Again, we have that national speaker coming in talking about winter pavement maintenance issues. All right, so Thank you again, panel. Thank you for joining us online and in person, and we hope to see you in an upcoming seminar. Thanks.